Bom dia a todos, o pessoal está entrando na sala. Guardar todo mundo entrar e a gente já começa. Vamos lá. Pessoal, mais uma vez, bom dia. Hoje a gente vai ter a presença, a palestra do professor Enzo de Sena. O Enzo, ele é professor do curso de áudio no Institute of Sound Recording, que fica na Universidade de Surrey, na Inglaterra. Ele vai contar um pouquinho para a gente do Instituto, logo mais, né? Mas ele é italiano, ele estudou na Itália, depois seguiu para seus estudos tanto em Londres, no King's College, como na Bélgica, na KU Leuven, que é a mesma da Mônica, que foi a nossa primeira palestrante, e passou também por Stanford e por Aalborg, na Dinamarca, e já desde 2018 ele é professor no King's College de Londres. E, bom, ele vai contar toda essa história um pouco melhor para a gente, e também sobre a Universidade de Surrey, o Instituto, e depois sobre a pesquisa dele, que é na área de reprodução espacial, focando em codificação psicoacústica, tá? Então, acho que vou parar por aqui. Enzo, first of all, thank you very much for accepting the invitation and for taking the time to share your work with us, and also to tell us a bit more about the University of Surrey. Please, the virtual floor is yours.
Thank you so much, Bruno, and yeah, thank you for inviting me. It's great to be here. Let me just start sharing. Let's see, can you see that?
Yes, we can.
All right. So Bruno asked me to just introduce a little bit the university, the research group, myself, and then maybe talk about some research. I'm going to try to be as quick as possible. I'm pretty famous for stopping too long on a slide, so I decided to have very few slides this time, and hopefully we're gonna make it on time. So as Bruno said, I'm a assistant professor at the University of Surrey, more specifically within the Institute of Sound Recording. And I just thought I would start with where is the University of Surrey? Well, we're based in Guildford, that's southwest of London. It's about 30 minutes train from central London. We have I believe, a very nice campus. It's very American style, with like a proper campus altogether, with a lot of green, and it's a fairly large one. Just a couple information: it was elected University of the Year in 2016. We have about 17,000 students, and we're focused both on teaching and on research. And in the latest, what we call research exercise framework, something that is a survey done on research. In the UK, every 5 years, I believe 78% of our research was classed as world leading or international excellent. Going down, I'm in the Department of Music and Media, although we're all engineers, and then down into at the institute level. The group is a leading center for research in psychoacoustic engineering, and I just copy pasted some stuff here, but essentially we work at the boundary of digital signal processing, which is really engineering based, and psychoacoustics. So we try to combine the two worlds of how we perceive sound together with how we can process it and have a proper solid mathematical framework for everything that we do. So that's really our area of expertise, is at the intersection of the two. And we use also, we use a lot of tools from other fields like statistical analysis. We do some software engineering, user interface design, and so on and so forth. And we are very closely aligned with the music department, and our students, they work both in the engineering and the music side. So we also have an understanding of the aesthetics of sound and music. We try to fit that into our research as well. We have some very nice facilities. Several recording studios at the highest industry standards. We also have some edit rooms, a listening room with a 22.2 systems, and a very large number of professional microphones. We also teach the main degree that our research group teaches is called Music and Sound Recording, also called Tonmeister, which comes from a German word that means the master of sound. And it was established, the degree itself, in 1970. It was unique at the time. Now a lot of people are trying to copy us, but don't tell anybody I said that. But a lot of people are doing something similar to what we're doing. And our objective is to train students to work in all areas of audio industry, from production to recording itself to design of equipment. And in order to do that, we give a mix of three things. It's a mix of pure engineering skills, also from mathematical and physical perspective, musical skills. So they also learn about harmony, for instance, and composition, and also from the operational engineering perspective. So we have some practitioners also that come and teach, for instance, electroacoustics and so on and so forth. We have, this I copy-pasted just the slides of our degree, so we have to, of course, show off our stuff. So we have an excellent reputation in the audio industry, especially in the UK. We have 97% employment rate, and we had a bunch of very impressive alumni coming out of the degree. Some that went on to do research and development. So, for instance, the head of research at Rowley, a popular company that does keyboards, for instance, was one of our former graduates, all the way to production and sound mixing. So we have had 3 Oscar winners, 7 Grammy winners, and 12 BAFTA winners among the students that attended our degree. So a little bit about me. Bruno already said a bit about my CV, so I don't want to talk about that. I just wanted to say how I started, and I think, like many of us here, I am just an audio and a music fanatic since a very early age. I like to organize a lot of parties when I was a kid, partly because of the social aspect, a lot because I just wanted to have an excuse to blast the loudspeakers, and I would just put a number of loudspeakers all around the room and have an excuse for that day to blast the loudspeakers without having the neighbors complain. So then I went on to study telecommunications engineering, because that was, at least in my town, I didn't have time to apply for the degree. So in Italy, you pretty much decide a few months before you start your degree. So at the time, I could not apply anywhere else. And the closest thing in my city, and at the time also in Italy, to audio was telecommunications, because the concepts are very similar. Electromagnetics and acoustics, they share a lot of features of both wave phenomena, and that makes them quite similar. So my research interests are in spatial audio, beamforming, and room acoustic modeling. I'm going to talk about room acoustic modeling today, so I don't want to say too much about that. But another one is multi-channel audio and spatial audio. That was part of my PhD work, where I wanted to make sure that people were perceiving sound in a loudspeaker arrangement coming from correct directions and in a correct way. And finally, also beamforming is the technique by which you can using a microphone, you can focus spatially in given directions, or make sure, for instance, that you hear something only in a given direction. But today I'm going to focus on this stuff here. And finally, as a shameless plug of my work, I recently got an EPSRC project. That's the Research Council in the UK, and I have a PhD position that is open, and actually it ends, the deadline to apply is on Friday. So Bruno, I hope you don't mind if I'm very shamelessly talking about this. So if you're interested, it's a
I've already spammed
all right, okay, all right,
with this position, okay. But please do that here as well.
So yeah, but that's all I wanted to say. It's a fully funded position, tuition plus salary. I think I calculated the amount of money between tuition and salary is about £100,000. So it's a very sizable studentship.
And that's for a year, right?
That's for 3. It's a fully funded PhD for 3 years.
I mean, the 100,000. That's for the whole.
It doesn't cost that much. It doesn't cost that much. So tuition fees, I believe they're around, I think around £20,000 a year, and salary, I don't remember exactly, but it must be around 15,000, 20,000. So something of that sort. And when you take them all together, the sum that I came up with Yeah, it is, was about that, 110,000 pounds. So,
Just
yeah.
because most of the universities most of the students that are attending here, they come from public universities in Brazil.
Right. Yeah.
But there is a big difference. I believe Surrey is also a public university, but
Yeah,
in the UK, they are paid. You have tuition, right? In Brazil, they are always tuition free.
Yeah, lucky you. Oh, maybe well, I shouldn't.
So. It's different. There are pros and cons for everything in life.
All right. So, are there any questions so far, or the next part would be more about the research? Are any questions from you, Bruno and William, or from any students?
Alunos, se quiserem, vocês podem interromper e perguntar aqui à vontade, tá? Just let me know that they want to make any questions, they can.
All right. If
I guess we can move on.
Yeah, let's move on. Let's see. Let me just share the talk here. All right. So
let me make one question before we start.
Yes.
Are there many international students at the ISR?
Yeah. So the degree, it doesn't have too many international students, and that is partly because we have very strict entry requirements. So I think we're almost as selective as Oxford or something, because there are so many students that want to come to our university to our degree specifically, but we're limited by the number of microphones that we have and studio recordings. So we're limited to 28 students. So that makes us, we can really very much select who we like, and we have very strict entry requirements with respect to which topics you've covered in your high school. So partly because of that, and partly because it's very popular in the UK, we don't have too many students in our degree, but in our research cohort, most students now are actually from abroad. So yeah.
Okay. Great, thanks.
All right. Okay, so as I said to Bruno, I just wanted to talk today about perception-based Soundfield synthesis. And let's see, I just want to really tell you straight away what the aim of this is. And the aim is to make you, the listener, feel transported to a different auditory scene. So imagine that you're playing a video game, and I want you to wear headphones, for instance, and make you feel transported to the middle of the shooting scene in a first-person shooter. Or if it is you're trying to estimate how a theater would sound like before you build it, I want you to wear headphones and feel like you're there, actually. Or in theory, a similar research strand would be on how to make you feel transported to another real space, like, for instance, in the middle of a football match. But in this talk, I'm going to focus on the virtual scenes. So you can see here on the left, imagine that you have a virtual room where you have a different number of sources, and I want you, the person, to feel as if you're in a specific position within that room while being in your real world with headphones, for instance. I decided to focus on headphones presentation because I felt it would interlock well with Jens' talk. So for those of you who were attending Jens' talk, he talked about binaural reproduction and how we perceive direction of sound and so on. So I felt like it would interlock well with all of that. And I'm thinking about applications here in video games, but also VR, AR, and as I said, also in terms of architectural acoustics. That is, if you want to predict how, for instance, a theater would sound like before building it. So there is a lot of people that I collaborate with, and their content also are fitting into the slides. I'm not going to go through the entire list, and also funding from several institutions over the years. So now, how do you achieve this aim of making somebody feel transported to a different space? Well, you have to do two things. The first is that you need to render the acoustics of the room. A given room will have sound travel and bounce within within the room in a very peculiar way, in a very specific way to the way that room is built, depending on its geometry, what the wall characteristics are, where in the room you are, where in the room the sources are. So all of this changes the way that the sound field, that the sound field behaves within that room. So that's the first thing you need to do. You need to simulate that. You need to try to estimate how the sound field will behave in that specific room. And the second thing, you need to oralize it. And oralization, the process of oralization is the equivalent of visualization, but just for the sound perspective. You need to make that sound field audible. That's the concept of oralizing something. And that is achieved by, for instance, emulating a certain head within the space that is then played back using headphones. We're going to talk about that just from one slide, actually. I'm going to focus mostly on step one, because at least it's my field. I feel like it's at least it's a more interesting problem, at least personally for me. Now, step one is sometimes it's not always recognized as being really important. Most people, a lot of people would just try to oralize something, sound sources, without rendering the room acoustics. And that has been done for a very long time, also in case of computer games and so on. But it is actually rendering the room acoustics is actually as important, if not more, as the actual step of oralizing. And that is mainly for two reasons. One is that it is in order to externalize sound, that is to feel like a sound source is outside from your head, which is something very common that happens when you wear headphones. It's like you feel everything inside your head. In order to externalize sound, to make it feel like really like that sound source there is not inside your head, is actually there in a given direction, it is important to render room acoustics. And there are a number of studies in the literature that have proven that externalization improves significantly if you include room acoustics. The second is that also the sense of immersion increases significantly. And that means we've recently done a student for their thesis, they've actually looked into this problem and asked people to wear VR headsets, and then we changed, we either included or not room acoustics, and asked them how immersed do you feel within that simulation of a space. And what we found was pretty remarkable, and that is that if you do not include room acoustics, in terms of feeling immersed, that has a similar penalty in terms of feeling immersed as reducing the video resolution by 80%. So we just made the resolution of the VR goggles drop significantly by 80%. And we found that having that drop in video resolution was equivalent in terms of loss of immersiveness as removing room acoustics. So that gives you an idea that how important really it is to render room acoustics. All right, so how do you render room acoustics? Well, over the years, there have been a very large number of models that have been proposed. I'm not going to go into the detail of all of them because there is really not enough time. So what I can do is point you towards some review papers, especially by Vesavalimaki and others in 2012 and 2016, aptly named 50 years of artificial reverberation and more than 50 years of artificial reverberation, and also a paper that we published in the Signal Processing magazine in 2017, looking more into perception-based models. So these three would give you a broader overview and a lot more information than what I can deliver to you today. Now, but just in general, I want to start from just the wave-based models and discuss why, especially for applications in computer games and VR, they're actually not that appealing. And although they're the most accurate ones, wave-based model, what they do is really take the wave equation and try physically to understand what happens in the room. And we have good models for how actually a wavefront and wave field would propagate in a room, and good models for also how the boundary works. So once we have that, we can try to solve that mathematically and obtain something that is physically accurate. So that is the most elegant solution you can give to the problem. Now the problem is, however, that this takes a lot of computational power to run. So if some of you have looked into the Nyquist theory, Bruno, has anybody you think? Yeah.
Several of the students.
Several. So yeah. So the Nyquist's main concept is if you have a certain signal with a given wavelength, you have to sample it twice. And something equivalent exists also for wave-based models, where instead of sampling in time, which you also have to do, but you also have to sample in space. That is, you cannot find the actual physical sound field on a continuous scale, because that would be impossible on a computer. You need to discretize the problem, and you need to take them two samples in space for every wavelength, and the smallest one. So for instance, at 20 kilohertz, the wavelength in space will be 1.27 centimeters. And that means that according to Nyquist, you would need to sample it every 0.7 centimeters, so a very small space. And imagine the room where you're in right now, and having to take a point every 0.7 samples would take a very large number of positions. So more specific, if you have a typical room of this dimensions, you would have 200 million grid points. And for instance, there are certain models that solve the wave equation that require 1 multiplying 6 additions for each of those grid points. And that means 70 billion floating points operations per second, which is many, many times over the capabilities of today's CPU computers, for instance, which are in the order of a few billion floating points operations per second. If you want to then render a larger space, this becomes enormous. It becomes 3 quadrillion floating points operations per second, and that is not feasible to do, at least in real time, which is the application that we think about in terms of VR, AR, and so on. It could take like hours or even days to run one of these simulations even on a powerful machine. So in general, although wave-based models are the best ones, and from the accuracy perspective, they're not really appealing from the computational perspective. So another class of models that was also up there was geometric acoustic models, which essentially make the assumption that sound travels like rays. So imagine that you have a room seen from above like this, and you have a certain source and a certain observer position here, and you have all these rays depart from the source. And then what you do is you trace them, hence the name ray tracing for this one. You trace them across the space until they hit the so-called the observer or receiving volume here. Once a ray passes through this receiving volume, you can record the time when that ray has arrived after leaving the source, and how many times has bounced off a wall, and that translates into what attenuation it incurred, and so on. And that's how you can build essentially an impulse response, right? A response to the output of the room for an impulsive sound source. So you can do also lots of things with this method. For instance, you can model diffraction. When a ray hits an edge, you can model it as if it is generating some more rays at the point of impact, and so on and so forth. This is a very flexible method that allows to include a lot of the physical phenomena that happen when sound propagates inside the room. And it has very significantly lower computational complexity compared to wave-based models. Now, what is the output of a model like that? An output of a model like that looks like this. We have a room impulse response, which Bruno, can I ask you also, how many people do you think know what an impulse response is?
Over the half, certainly.
Okay, all right.
If you want to discuss very briefly what that means, please go ahead.
So an impulse response is, as the name suggests, is an impulse, is the response of the room to an impulse. So imagine, for instance, that you are in a room and you clap your hand, and then you record the output of that hand clap. And in fact, if you just give me a second, I can actually share something along those lines. Let's see. Oh no, I have to share the sound. So this is very impromptu stuff. So let's see. Yeah, just an example. Can you hear that? So this is an example of an impulse response in a church. So again, imagine clapping your hands, and this is what you would hear. In a bathroom, would sound like this. So it's a lot shorter. And this is an example of this lasts for 75 seconds. So yeah, I'm not going to play it all, but this is the world record for the bicarbonate of oil storage. You can see it's a very large space with very little attenuation. So that what causes that very lush and very long impulse response. So now an impulse response, if you plot it, it looks like something like this. If you plot it in terms of dBs, versus time, you have a certain direct line of sight. Then you have some early reflections, which are sound that bounces off a wall maybe once or twice. And that depends on the definition of early reflection is not univocal, but it's defined in terms of timing. And then you have, as the number of reflections from the walls increases, then you start to see something that looks like this. We call it rate reverberation. It starts to behave stochastically, randomly, really. Now, the early reflections are very important perceptually, along, of course, with the direct component, to have correct, give a correct impression of the size and the shape of a room. And the late reverberation also is important, mostly for the size of the room. It's also used, all of this also to estimate the distance of a source. We call it the direct to reverberant ratio. So there is no time to go too much into detail, but I just wanted to show you how an impulse response looks like. Now, how do we use the impulse response to generate the output of the room for any other input? Imagine that you have a source which is, well, a shot would be very similar to this, but imagine that instead of wanting to generate a shot or a hand clap, you have somebody speaking in front of you in the video game. How do you render the output of the room for that sound signal, where it's fairly simple? Well, I mean, there is a lot involved, but essentially you can use the impulse response is all you need to generate that. And that is achieved by calculating the so-called convolution between the impulse response and your sound sample, the person speaking, for instance. Now, convolution, however, is also an operation that is not really all that cheap from the computational perspective. It still takes quite a few resources to calculate that. So for instance, if you have the reverberation time, that is the length of the impulse response, imagine the one very similar to the church that we heard before. If that's the length of the impulse response, you have a so-called sampling frequency of 50 kilohertz, and you have 3 sources and 2 listening points, like 2 years. This would already take 60 billion floating point operations per second, which is, again, many times over what you can do with today's computer. There are several ways to make that a little cheaper, but it's still expensive from the computational perspective. Okay, so there is another approach to the problem, which avoids completely calculating geometrical acoustics or calculating wave base or calculating convolution even. And that is by using what we call some recursive filters, which are very popular in digital signal processing, where imagine that you have an input signal, so an audio signal coming in here, and then what you do is you spread it out in a network that looks like this, right? You send that signal. Imagine, for instance, the person speaking to you in a video game, and then this is sent out to another point within the network, which then with a delay of say 107 milliseconds, and then this is then spread across all these other points. So it's sent to all the other directions. And you can imagine that very soon you have a number of different streams going all around this filter. And that increases, essentially models the number of echoes that you get when you have a number of reflections in a room, in a way. So this is a way to just perceptually to render something that sounds like reverberation, like the one that you heard earlier. So this specific model, as I said, it's called digital waveguide networks. And in this network, you can choose a different topology, right? Imagine that this signal is spread to all these directions, but then maybe one is not connected to 3, you could connect it to 5, for instance. So the topology of this network is a degree of freedom for you. You can choose based on certain objectives that you might have here. And also the length of each of these delay lines, of how much each of these things are delayed, is also a degree of freedom. You could choose it however you want. And also what the specific operation that happens when they hit these points, these nodes, is also a degree of freedom for you. So the question is, how can you set these parameters? And a model that we proposed quite a while back, sorry, now it's called the scattering delay network. And this is a way to design all those parameters based on the way that an actual room is built like. So I'm going to focus here on this plot and try to walk you through a little bit. So you can imagine, you see here a room seen from above, okay, where you have a certain sound source, a certain observation point. And each of these lines, they correspond to a delay line, okay? A delay line that essentially all it does is really to take a certain sound signal and delay it by a certain amount, make it come later in time. And the delay that happens here in time corresponds to how long in time, it corresponds to how long it will take for a sound wave to travel from the source to this point, for instance. So that's how we represent these things. This is the delay line that is that you can see it in space. So sometimes it causes confusion to somebody, but essentially just exactly the same as before. It's just that the length in time, the delay in time, corresponds to how long it takes for a sound wave to travel. And as some of you know, sound travels at 340 meters per second, a little over than 1,000 kilometers an hour. And so you can always calculate, based on a distance, you can always calculate how long it takes for sound to travel between different points. And I don't want to go too much into the detail of all of this, what's happening here. I just want to focus on a few things. Each of these lines here represent a delay line. And these nodes here are the same nodes that you saw earlier. And their position their position is not random. Their position here is exactly at the point where a first order reflection will happen. And what is a first order reflection? Let me see if I can draw something here. So first order reflection in this case is this reflection here. No, I don't want to go into the other side. Yeah, okay. Imagine that that's a, okay, maybe I can try to redo it. Right, so a first order reflection is imagine again, like the rays that we had earlier, and it's sound that bounces off the wall and arrives at the position of your observer position. And the way that this ray looks like is such that the angle here and the angle here are identical. That's what defines a first order reflection. So I'm positioning the scattering nodes here. We're positioning scattering nodes here such that this delay line and that delay line actually correspond exactly to that first order reflection. So let's take a look at, let me just mouse here, go back to this. So let's take a look at how actually, what is the effect of making this choice on the output of this network of delay lines, essentially. And the effect is this, that if we have, because we have exactly that, those delay lines correspond exactly to how a first order reflection would sound like, then at the observation point here, we're going to exactly observe the first order reflection is going to be rendered exactly here, okay? And so that's all fine and good, and this is the same for all the other walls here. So it's not just the first order reflection associated to this wall here, it's also the one associated to this wall, etc. So let's see what happens, however, for second order reflection. That is reflections that bounce not off just one wall, but off of two walls, like this one here, for instance, or this one here. Now, the delay lines included in this model, in this network, they don't contain exactly a path like that, right? There is no path in that network that corresponds exactly to this second order reflection. However, However, there is an approximation of it, right? This second order reflection is approximated by this yellow one here, right? So this, or orange, I'm not really sure what color is this. But it's corresponds, it is, instead of being exactly a second order reflection, it is approximating that second order reflection. So in other words, at the observation point, we are receiving, because the sound is delayed by this amount, and that amount, this very closely resembles the delay of an actual second order reflection, which is the blue one. And this depends also on which specific second order reflection you're picking. So for instance, this other second order reflection, the blue one, has a worse approximation here, but still this yellow path does correspond somewhat to the actual second order reflection that we have. So what does that mean? That essentially means that first order reflection, and I didn't say, but the line of sight is also exact, which is very good from the perceptual point of view, because as I said earlier, early reflections are more important perceptually, whereas the second and higher order reflections that you have are being approximated with worsening quality. So there is a gradual worsening of the approximation of higher order reflections. However, it's been shown that the exact structure of the exact time structure of the late reverberation, that is of higher order reflections, is not that important. So one interpretation which is pretty tricky of this model is this one here. You're seeing now a room and a network of tubes. Now, this is of course a rendering. I didn't actually build this, but this is essentially, we've shown, and this is a second interpretation of the model that I've just shown you, that that model that I've talked to you about, this network of delay lines, actually is a physical model for a network of delay tube, of a network of acoustic tubes like this one. So essentially, instead of simulating exactly how sound propagates in the whole room, I'm simulating only how sound would propagate inside a network of acoustic tube like this. So in other words, the model that I've shown you earlier, just one slide earlier, actually, if you were to put your head where one of these black balls, this sphere represents the source and this sphere represents your observation point. If you were actually to put your head within that sphere, you would hear something that is essentially the same as this network here. So essentially this model, instead of simulating the full propagation of sound in a room, it's only simulating this thing here. And you might ask why. Well, the reason why is that this is extremely fast. This is just some delay lines which are implemented as circular buffer, and then some multiplication. So it's extremely fast from the computational perspective. It's actually thousands of times faster than a wave-based simulation. It's about 10 times faster even than just convolution alone. And that is the main advantage here. Now, the key, however, is that, so you might ask, yes, but it's going to sound like in a network of acoustic tube. It's not going to sound like an actual room. So what's the point? I'm not going to fool somebody to believe that that's an actual room. It turns out instead that the network of acoustic tube and the actual room, they share a number of very important features of acoustics. Like, for instance, the length of the reverberation, the length of the impulse response. In other words, for how long a room continues to reverberate, we call that T60. It also has a similar buildup of the amount of echoes that you get in a room. It also has things called axial modes that are similar. So there are a number of things that make perceptual sense, and they're very similar between the full room and the network of acoustic tubes. Okay, we've also shown, and I don't want to go into the detail of this, but we've shown that even though it's a lot faster, it's also perceived as being slightly more natural. So compared to some other state-of-the-art method, but I don't want to bore you with plots. What I would like to do is try to get to a point where I can give a demo of this. But before that, I would like to make a link with what Jens has been talking a few weeks back. And that is, how do you then oralize? How do you then render over headphones the output of that network of acoustic tubes? And the way that you do it is using something that I believe you mentioned, which are head-related transfer function filters. And that is essentially, it's emulating how sound will behave and diffract around your head and arrive slightly later at one ear than the other, with a slightly different level depending on the frequency. All those things that were discussed earlier, you can do it also in this model. And the way you do it is this. Imagine that you have a virtual listener, like a virtual head oriented in a given direction. And what you do is exactly the same things that Jens has been talking about filtering sound, because you know the directions of the incoming delay lines. So you know that there is a delay line coming from this direction, this direction, this direction, this direction, and you know what their angles are. So you can pick the head-related transfer function filter in that direction and render it like so. So, and then you can do that for different sources. I'm going to show you a little demo of something that implements all of this stuff here. Also, if the virtual listener is moving their head, then you can also just update this. So it's head tracking is also relatively simple to do in a model like this. Again, because you know from which direction the delay line are incoming. Okay. All right, so we've been using this in a field in a number of scenarios. We've had it used ranging from a beatboxer at Somerset House. We used it together with some theater performers at RADA. We used it at the Guildhall. We used it with a very famous piano player, Yuja Wang. And more recently, we have at the National Gallery, there is an exhibition that is using our technology to render sound, to make you feel transported to a different space. All right, so the last thing, I know that it says 18 slides, but likely for you there are references at the end, so we're essentially done. And I believe we do have time. Bruno, is that okay to show some demos?
Please do, yes.
Okay. Fantastic. So I'm just going to set it up. In the meantime, for those of you that don't have headphones, if you can just pick them up, and because these are like Jens' demos, these are also what we call binaural demos.
That's the future, right? We are going to be living in a binaural world pretty soon. So
yeah. Yes.
Well,
there is. I mean, there is a lot
for a year now.
Did Jens talk also about crosstalk cancellation, or did he not?
No, he didn't mention that.
So yeah, there are just also methods that achieve the same result, right? Of making you feel the binaural experience, but just using loudspeakers. So hopefully we're not going to be obliged for the rest of our lifetime to wear headphones all the time.
Yeah, I know. Filippo is working on that.
Yes,
should invite him for the next round.
Indeed, yeah, indeed.
But I know he has two little kids right now. I thought maybe it wasn't a good idea to invite him at the moment.
Yeah, he has his startup as well, so I'm sure it's a bit difficult. Okay, let me just because I'm lost here. Presentations, Campinas, yes, final. Okay, so I am going to start with this one here. Oops. I don't want that. I also don't want Apple software to play this back. Let's try with QuickTime. Okay, I'm also going to activate original sound so that you can have the binaural experience. This might cause some echoes, a little bit of noise, but hopefully it's not too bad. I'm going to also I'm going to mute myself so that you can actually hear the experience, and that's it. Bruno, I think there is some noise coming from you now. So maybe if you mute yourself as well, maybe it's, yeah, thanks, that's perfect. All right, so let's take a look, and please nod if you hear.
He stole a kiss in the changing of the reels.
So yeah, so this was the audio stems were taken from this paper here. I have some colleagues at the University of Surrey Technology for this samples. And here what you have is different sources in front of you. The whole band was associated to each of these dots, and the singer was with the blue dot. And I also wanted to just show you some rendering of distance here. I'm just gonna play it again for a second.
He stole a kiss in the changing of the reels.
This is something else that also is needed to, it's necessary to render room acoustic to render the sense of distance, because one of the main features is how much direct energy is coming with respect to how much reverberant energy is coming, and that is inherently related to room acoustics. Let me also show, I have another short video. Let me just open that up. This one here. So I'm just gonna play that. Again, let me know if you can hear all right or not. So yes, so those are the two demos. Just before concluding, I just wanted to show you another one where I'm actually going to try to challenge you to hear the difference between different types of models. And some that are very accurate from the perceptual perspective, and some that are not. So I'm just going to play this. It should be fairly straightforward. This is 2 minutes video, and then we're done. So the one you just heard was a physical model, very accurate and very complex. This was the faster network of acoustic tubes. And this was a geometrical acoustic method, the one similar to the one ray tracing based. Just with the difference that the first and the second, one was 7,000 times faster than the other. All right, so just to conclude, what have I talked to you about? Just one main idea that if there is something to remember out of this is the idea that you need to render room acoustics if you want to really deliver a convincing VR, AR computer game experience. And that is in order to feel externalized and immersed. Then we made an example of how physical models require significant resources, and how you can leverage perceptual effects to reduce the competition requirements. So that's it. I just wanted to thank specifically Zoran Cvetkovic and Hussein Abiboglu, who are my main colleagues for all of this work. We've also given an ICASP tutorial a few days ago, and I believe one slide was coming from that tutorial, so I just wanted to thank them. All right, that's all from me.
Thank you very much, Enzo. Really interesting. Really like the quiz you made with the different renderings and how they sounded.
Yeah,
I did guess, however,
Oh, you did.
I listened. I noticed the difference between the three of them. I didn't know which one was that, but I rated them in my mind.
Yeah.
And the poorer sound was the SDN.
Ooh. Well, I'm glad to tell you though that not everybody think like you do. So, but yeah,
you know what? For me at least, the difference was there was more. The bass wasn't as defined.
Yeah.
So it was a question of low frequency definition. Yeah. I don't know if you looked into that. Did somebody else say something like that?
So we looked into the model behavior of it, but not very closely. The main idea here is that because you have certain delay lines that are parallel to the room axis, these delay lines are going to have resonant frequencies that are similar to the resonant frequency you would get in a room. So it may have to do with, I mean, the model behavior. It may have to do with what you heard, but I'm not really sure. But
because the idea of it's really clever. It's so smart, right? I think of it. Can it be that we're thinking of a lumped element model of the room?
Yeah.
Like a concentrated element model. Instead of simulating the whole wall, I'm substituting the wall by a point.
That's exactly right. Yes, absolutely. It is. And my work going forward is to look exactly along that line of thought. So it is absolutely like that. Yes. Okay. And that is also what allows it to be extremely fast in this version here. So yeah, absolutely.
And you might probably in the continuation of your work, you might find limits where this lumped element will work
or doesn't work. Yeah, absolutely.
We're both from telecommunications. We know that this been on going on forever, and in the telecommunications, they know up to what point they can use lumped models or not. You might get to this limit as well.
Yeah. So it's a very interesting question. First of all, there have been Stevens and others, I believe with Damian Murphy and was it Vesa Valimaki as well? They looked into a second order version of this, so using 2 points per wall instead of just one. So this has been extended in that direction as well. But you're absolutely right, and the main question then is how important it is perceptually for that lumped assumption to be invalid, and how important it is physically. So there is also these trade-offs between a perception and physical accuracy that come into play. So yeah, very good point. Yeah.
Cool. There is one question from João. João, do you want to open your mic, or should I?
Yeah.
My network is a little low. I have some falling signals.
We are listening to you. Go ahead.
So I want to know how it is related, the difference between the T6's frequencies. If it is a measurement that is a mixed model of the impulse response and later the reverberant tail to give this feeling of reality, or is just made in the network of delays? And also, if the second question is what is the node point spatial resolution? If it has you have to give a lot of points, right? So how it is the minimum distance between it?
So starting from the second one, what do you mean a lot of points? Do you mean, are you talking about now the wave-based model or this network of acoustic tubes model?
The network acoustic, but you have reflections all over the wall, right?
Yeah, but they're all bundled. They're all bundled in one single position. So effectively, you do not explicitly model any of these. So that's the key idea here, that this is just really all that is happening is in between the scattering points. So we are approximating all the reflections using only those points on the wall. So that's the main idea. So you don't actually have to calculate any of these reflections. You really run this network of delay lines as it is, which, as I said, it's extremely cheap competition. Does that answer the second one? Yeah. So the first one, was it about frequency dependency?
Yeah, it is.
And the frequency dependency is T60, right?
Yeah.
Yes.
So yeah, we in here you can essentially, what we've done is you could run a bunch of SDNs at different frequency bins and then bundle them all together, but that's not necessary really. What you can do instead is every time sound bounces off the wall, and that is every time it passes through one of these nodes, you apply a certain filter, a frequency dependent filter that corresponds to the absorption characteristic of the wall. So there are certain databases available of the absorption for different materials, like cotton carpet, for instance. And then what you can do, this plot, we've shown that if you do put those filters in and then run in the time domain, this is all a time domain method, this network, then the reverberation time that you obtain, which is on the y-axis, x-axis is frequency, is very similar, for instance, to Sabin equation, which is an approximate measure. But this gives an idea that this does indeed allow you also to have the correct or approximate reverberation time as a function of frequency as well.
Yeah.
Very good.
Thanks. Very interesting lecture. And I see that you work with Julius Smith, and I was wondering if it is some Faust code, maybe you know it, that implements this. I know they have some FDN delay implemented. And
yes. So Julius is a big fan of Faust. So yes, we collaborated together on the main paper here. It's a transaction paper. And I don't believe he's worked on a Faust implementation. What we do have is a MATLAB implementation, which I can share with you. If you send me an email, I can point you to it. It's on my GitHub. So if you look up my name and surname and then GitHub, you should find it out. But it's extremely slow because I just had to write it without any care about how fast it would be on MATLAB using object-based, and that took forever. Or we have a C++ implementation, which is real-time, actually a lot faster than real-time, and that's what you heard from the demos. But that's not available publicly, at least at the moment. We're thinking about it, but it's not public at the moment.
I see. Nice. Thanks.
No problem. Thank you.
And so I have. Please go ahead.
May I? No, I was just wondering how fast is fast that you showed us in the last quiz, and I was wondering to ask about this auralization engine, if available, but I guess it told us it's not available. Is that the same?
So absolutely. So the first question, this is a plot that shows the computational complexity in terms of floating points reverberation per second of SDN of this network as a function of the reverberation time. Because of the changes in terms of reverberation time only reflecting the length of the delay lines, actually changes in reverberation time do not affect SDN. So that's why it's a flat line. I just added it. And then you can see this red line here is overlap add with a static. So assuming that you already know the impulse response of the system. So with some other way, you have to calculate impulse response and then run it. So even convolution is about an order of magnitude slower than this overlap had. So FFT based convolution. So that's about an order of magnitude faster for reasonable values of reverberation time, like half a second to 1 second, for instance. Then on top of that, you need to add the complexity of actually calculating an impulse response. And if you have to do it dynamically using, for instance, the image source method, this is what you get. So a couple of orders of magnitude. There are faster ways than this, but this was just like what we had in the paper to just give an idea of the orders of speed. Does that answer this question? So now, practically speaking, we have an implementation I can share with you. If you send me an email, I can share with you a demo of that plugin. It's a BST plugin. We also have a Unity plugin if you want, but it's also, that one is not public yet. But we're really happy to send it out to somebody who can give us some feedback. So
that would be nice. I definitely send you an email. Thank you. Grazie.
So yeah, and in terms of practically speaking, a VST occupies about 1 or 2% of a modern CPU. And I mean, we could do better but there are diminishing returns with optimization. So it's very expensive to have code run really fast. And we think that 1 or 2% is okay.
Yes, definitely. Talking about practical stuff. So what is limiting, what in your opinion is limiting the mainstream video conference systems like Zoom or Meet or Teams to use such include reverberation to give a more realistic sound, since we are most of us are using headphones the whole day anyways.
So that's an excellent question, and one you should ask them, because everything is in place. I think that things are happening. Spatial audios just had a very big boost by Apple. Now they're releasing many songs using spatial audio, and also supporting the new operating system we just reviewed yesterday is going to support spatial audio also, just if you use headphones on your operating system. So things are happening, and the AirPods also have head tracking, so you can also render binaurally and so on and so forth. So things are happening. A question of why they haven't done it, I ask that myself very often. They do have on Zoom a feature on like a virtual room type thing, but I'm not entirely sure how. I actually never tried to use it, and I don't know if that includes spatial audio. I think it should, but yeah, I'm not really sure.
Yeah. Good. Danielle wanted to make a question. Danielle, please go ahead.
Yes, Enzo, thank you very much for your presentation. And I want you to ask, you talked about the WWDC event yesterday. Yeah. And I would like to ask you, what is your opinion on the Dolby Atmos used by Apple in the Apple Music streaming service?
Yeah.
In the point of an actual researcher and.
Yeah. So you see, the Dolby Atmos is I mean, I don't know a lot about it, and that is partly because by design, because a lot of the things that they do, they actually don't publish. So
we don't know what we do.
Huh?
We just don't know what Dolby does. That's part of their business.
So it's difficult to tell how they work, what it is that they're doing. So yeah, it's very hard for me to answer that question. But yeah, I think one worthwhile direction is to actually test these things out objectively through perceptual listening experiment and see what happens compared to other stuff. But yeah, it's difficult to know and for me to say anything about it really. I mean, in a way, I am happy, because if the world is paying attention to this stuff, if Apple is investing money into spatial audio, it means that probably people want it, and you know, this is binaural technology has existed for many decades. So the fact that it is
100 years.
Yeah. So you know, exactly, yes. So the fact that it is happening now at the highest commercial levels, that I'm actually just happy about it. But yeah.
Mm-hmm. Yeah.
Let me make one last quick question, and it has to do with when you said perceptual evaluation. In the very beginning of your talk, you were saying that you asked people on, you were comparing the quality of the audio with quality of video, and by asking how immersed they felt. So
Yeah.
how do you make that question? How is that you evaluate immersion?
Yeah, it's not an easy point. I mean, we're about to send a paper out of that, and I can send you just the archive version. That's what we're planning on doing. But let me see. But there are certain definitions that have been given. So I mean, there are several ways. There are actually tests for immersiveness, or you just ask them a question that is properly framed, and that's the approach that we use. We gave them a definition of immersiveness, and we asked them how after that we asked them how immersed do you feel. So that's mostly so of course it's something that is self-reported, but yeah, I'm not entirely sure if I can in real time just find you the definition that we use. Probably a little bit difficult. So yeah. No,
don't worry. But the main point is you asked the question, and it was self-reported. We were indirectly measuring immersion somehow by tracking or anything like that.
Yeah, okay. I guess there are other ways to do that, but that's just.
I was asking because I have a student that's looking into that. So.
Oh, I see. Yeah.
Good. We are 10 minutes over. As I said, we always have good discussions in the end. And if we can keep on going. I think it's time for us to resume. And once again, I want to thank you very much for taking the time and the effort to participate and sharing your experience and your research with us.
Yeah.
Grazie.
All right. Okay.
Thank you so much.
Obrigado.
Guys, todo mundo abriu o microfone e dá um aplauso para ele. Hand of applause.
Thank you so much.
Yeah. Have a good day, everybody. Bye-bye.
Bye-bye. Bye.
Bye. Ciao.
Ciao. Bye.